Okay. So let's see an example. We said that whenever we try to design an antenna, we had to give two values. Okay. This is what we have to consider. What are these? The number of elements and the ratio between the major lobe and the secondary lobe. So here we have n equal to 10. Secondary, this is the ratio between two subsequent lobes, the major and the other one. So once we give these two values, we have to provide all the different coefficients and the excitation coefficients for all the different antennas, which are put into one array. So that's good. We were given the ratio, but this was in decibels. If this is in decibels, we want to convert this one as a voltage ratio. So once we convert this as a ratio, we get a value which is approximately 20. Okay, so let's assume that's 20. We take it for that. Secondly, we said that the number of arrays is going to be 10. If the number of not number of arrays, the number of antennas into an array, it is 10. That means that P, which is going to be equal to the order of the Chebyshev polynomial, it's n minus 1. 10 minus 1 is equal to 9. That's good. Once we observe an nth order of Chebyshev polynomial, that means that the polynomial is going to look something like cosine, cosinusi in nant omega then. Nant fishy, a fundamental frequency which is in there. So we get a ninth order Chebyshev polynomial, and then we have to determine what is at Z0. And in order to determine the Z0, we have in fact, we kind of skip this one, not skip, but this is described here, what the Z0 is going to be equal to. So Z0, we can see what that belongs. So Z0, this is how it is described, and again, this R, this is equal to 20. That means that 20 squared is 400 minus 1. This is 399. 399 square root. This is some number smaller than 20. So here we have 20 plus almost 20. This is in the order of 39, but less than 40. And then here we have 20 minus around 20, so this is around 1. So we have 39, approximately 39, to the power 1 over p, plus 1 to the power 1 over p, and 1 over p, it is 1 over 9, okay? So then the Z0, this is what we obtained for Z0. And yeah, so these numbers that we're talking about, yeah, this is, so we just substitute them here. This is what we get for the Z0. And let me think for a moment, yes. $334, $333, yeah. Okay, so we are determining this Z0, and this is, we can skip this one. And the ninth order Chebyshev polynomial, this is what it looks like. And ninth Chebyshev polynomial of ninth order, we know that it's an odd function. If it is an odd function, it is, this is how it should look like. It's something like, so for odd functions, let's not, wait a second, so what is this? Plus 1 minus 1. So if y is equal to x, we know this is an odd function, it looks like this. If y is equal to x cubed, it's going to look something like this, I believe. But if it is, so we have this kind of anti-symmetric symmetry. So, and now, let's not forget, we said that these Chebyshev polynomials that we see here, this will be evaluated as a function of z. And these values of z, what we'll really care about is that z should be equal from -1 to 1. But we can have a look at how this Chebyshev polynomial can change even for z larger than 1. Okay, but let's see this one when it comes with an example. Now this is the Chebyshev polynomial. The magnitude, this is how it looks like. The magnitude is somewhat, so is the amplitude. Let's call it amplitude, not the magnitude. So, and looking at this graph, this is essential to describe D equal to NL size systems. Yeah. So we'll talk about again this later. And now let's try to have a look at now. Things will become a little more clear now. We said that the array factor, when we have 10 elements, it's going to look like this. AF 10, this will be equal to the summation or linear combination of 5 different terms. Let's not forget the number of terms. It's always divided. It's almost half of the number of antennas in the array. So here we get A1 times cosine U plus A2 times cosine 3 times the fundamental frequency. So let's assume that fundamental frequency is U, and then all of the subsequent terms will have the fundamental frequency times 3, another term which is cosine of fundamental frequency times 5, fundamental frequency times 7, and finally times 9. And now this is the array coefficient, okay? Sorry, the array factor. And then this array factor, at the same time, it will be equal to the Chebyshev polynomial. It's really a very good coincidence, and also a very good derivation of these beautiful polynomials. So essentially, what you might expect, because when I was trying to describe the steps needed to determine what should be the design of an antenna, in the end, we are interested into obtaining what are these A1, A2, A3, A4, and A5, right? So that's what we cared. So so let me think for a moment. So this is Z, right? And this is Z to the power 9. And this is cosine U, and this is cosine 9U. Now, what we will do is that this cosine 9U, we want to describe as a function of the fundamental frequency, and this one is done here. Okay, so cosine 9U is equal to 256 cosine to the power 9U minus 576 cosine to the power 7, and so on. So for a moment, let's have a look here. This is cosine 3U. Cosine 3U, it includes cosine U, right? And it has cosine 3U. Let's put 3 lines. Cosine 5U, which is here, it includes the cosine U, okay? It includes cosine to the power 3U, and it has also, let's put this with a square, cosine to the power 5. But then here, cosine 7U, it has the fundamental frequency. It has so this is cosine to the power 3, this is cosine to the power 5, and the cosine to the power 7. So let's use different notations. We come back here, fundamental frequency, cosine to the power 3 with an ambisome here, cosine to the power 5, we use like a square, cosine to the power 7, we use a triangle, and cosine to the power 9, let's use a square. Okay? So what we want to do, and let me try to explain, is that this array factor here, this is cosine 9U times A5. So let's add here A5. Let's multiply it. Then cosine 7U times A4. So this is the fourth coefficient. Cosine 5U, this is A3, and so on. So in the end, well, let's do this one. We're almost there. Cosine 3U, this is equal to A2. So let's multiply it by A2. And we need to multiply it by A2 also on the other side of these expressions, right? So then we are going to notice that we have minus A2, minus 3A2 plus 5 cosine U minus 7 A4 cosine U again, and so on. So we're going to collect like terms. Then here we have cosine cube, cosine cube, cosine cube, and this is also cosine cube. Then cosine to the power 5, cosine to the power 5. Where is the rest? I cannot see it. Cosine to the power 5. Here there is another cosine to the power 5, and so on. Then we have here cosine to the power 7. This is again cosine to the power 7, and so on. So it looks like when it comes to A5, in order to define A5, we get here, well, we're going to look at this term, and I cannot see it, and this term, yes. So, or this and this. Let's move ahead. So, again, so let's say we said that Z0, we need to find it, and then we calculated this one before a while. Then we said that the cosine u, it can be described as z. And let's not forget, when we derived the Chebyshev polynomials, we had over there that cosine alpha, it was equal to z, right? So again, we have the same similar expressions of the cosines. So that's how they look like. Then we add up together these terms, okay? And then all we have to do is that this side of the array factor, we have to equal these with the 9th order Chebyshev polynomial. It's something that I kind of said so far at least 2 times. Then when we get these terms, so this is z, okay. So, and then we have to equal terms with equal z to the power n. So here we have z to the power 1, and this is also z to the power 1. This is z to the power 3, and this is also z to the power 3, and so on. Once we do it, we're going to have the following. 256a5, let me try to see it here. 256 a5 times z to the power 9. Now, so this is going to be equal to this. And this z, in fact, this is going to be 1.085. And let's see where we have it. 1.0. I thought we looked at it at this one this way. Yeah, here we are. So this is the Z0. 1.08. This 1.08 times to the power 9. Okay. Apparently, it is going to be equal to. Wait a second. No, Z0, we have it over there. But this will make possible for us. So actually, this is again Z0 1.085. If we substitute this number into Z0, we get this. That means that A5 is 2.086. A4, it's equal to 2.83, A3, A2, and A1. So all of these we have obtained from the array factor, equaling that to the Chebyshev polynomial. Now, these values of the coefficients, we can normalize them, and the normalization, it simply means dividing by by the value of A5. And we can normalize this into 2 different ways. We can normalize with respect to A5, or we can normalize with respect to A1. Okay. Now, using the normalized coefficients, the AF, this is what it is going to look like. So finally, we have an array factor, which looks like this. Now that we have this factor, it is relatively easy for all of us to determine the angular distribution. Okay, and also a small reminder is that this u, it is equal to pi d divided by lambda cosine theta. Okay, so and again, you can always remind yourselves of why such an expression appears here, and I think we talked about this one in a couple of slides before. So this was the term which appears like cosine. What was it? Kd cosine theta minus beta. So that's where this d and lambdas should appear. Now, this angular, not angular, this AF is not angular, it's array factor. This array factor, this corresponds to the drawings which are shown here in this figure, when the wave d is equal to a quarter of a wavelength, and whenever d is half of a wavelength. So these are broadside antennas with the respective decibels, or with the respective ratio between the fundamental lobe voltage to the secondary lobe voltage ratio. Okay. So this example is over. Now the array factor patterns of example 6.9, they are shown in the slides here for lambda, a quarter of a wavelength and half a wavelength. Now, since the spacing is less than 1 wavelength, which we mentioned before, that this is relatively critical. So often the spacing should always be smaller than lambda, because otherwise the antenna, it will exhibit unexpected patterns. Now, as long as d is smaller than lambda, the maxima exist only at theta equal to 90. However, when the spacing is equal to lambda, 2 more maxima appear. Okay, I think we have talked about this one since the last time. Now, for d equal to lambda, this specific array, it has 4 maxima, and it acts as an end fire as well as a broadside array. So it's going to have 2 maximas on top and 2 maximas on the side. And now, Now, formation of the pattern. So we said that the ratio between z and z prime, z0, this is equal to the cosine u. So this is somewhat equivalent to, how we can describe this, cosine u. So this cosine u is going to look something like this. So z divided by z0, where z0 is going to be the hypotenuse. Now, this in this expression, for d being a quarter of a wavelength, only we're going to use the Chebyshev polynomials, for which z is between 0.76 and 1.085. Okay, so this is something that we have to be careful about. So let's have a look again. So when d is equal to lambda over 4, we have to include the Chebyshev polynomial, which is where z is above 3/4. So now this one, we're going to, so let's have a look at these values, okay? And let's go back and try to figure out what we are talking about right now. So we're going to consider, so that Chebyshev polynomial is actually higher than a. So this a that we see here, this is, I forget what that was. This was z0. It is, or z, it is 0.7673. Okay, so this is, so this Chebyshev polynomial, we have to look in this regime, okay? We're going back and forth, but so again, we are still dealing. So now let's remind ourselves, what was this Z0? This Z0, it was when n was 10, and what was the other condition? And then the voltage ratio between two subsequent lobes, it was equal to 20, okay? So this is, we're still talking about the same antenna, and at these specific values, these are the Z and the Z0s. So really, Z0 is like an hypotenuse, that, as we try to draw here, and the rest, so this one is in fact Z0 times Z over Z0. Okay, so this one, here there is some intuitive approach how to do this. So we have Z is always Z0 times Z divided by Z0, right? So in principle, we are multiplying this one by the cosine, okay? And then for this specific antenna, let me think for a moment what this represents. I forget. Let me have a look at my notes. Wait. Okay, so for this Chebyshev polynomial, we have to look at three different z values, and these three different z values, we see that z increases. So at this stage, we have to think about. So we say here, we have to think about the Chebyshev polynomial, which it was 9th order. It goes something like this, and also like this, and something like this. So at this Chebyshev polynomial here, what this is telling to us is that for a specific antenna, given these two parameters, we have to consider that this Chebyshev polynomial is above 3/4 and a little above, okay? Because this goes a little higher than 1, which is 1.08. Now here we have another, and by the way, when d is equal to lambda over 4, we are talking about point A. For a moment, let's remember this was point A. Here, we have to consider point B in a specific figure. So we observe that at this d over 2, the Chebyshev polynomial that is used, it is mostly in this domain, between 0 and 1.085. So if we go back here, we're talking about, in the first case, when d was 1/4 of a wavelength, we were analyzing only this region. Okay, so actually this is higher than 0.06369. In the second case, we observe that the values of z, they can be from 0 to 1.018. So this was point A, and let's call this one point B. And let's go back for the last time. Okay, so I'm taking back and forth. So here we have point A, which works as, this is point B, this is point C, and this is point D. So now the Chebyshev polynomial. So reminder, this class needs a lot of reminders actually. Even myself, I get confused very easily. But it looks like for an antenna where the spacings is equal to half a wavelength and n is equal to 10, and the voltage ratio is equal to 20, we know Z0 is 1.085, and the value of Z, which we're going to evaluate this Chebyshev polynomial, is going to be for regions higher than point B, which is from 0 to 1.085. Now, for a different antenna, which is a little longer, then we're going to observe as, wait a second. So we're going to evaluate the function from minus 0.7 to 1.08 to minus 0.76 again. So you may think about this one. The Chebyshev polynomial is defined from -1 to +1. But here, this antenna, which is given with this wavelength, we are going to read the values. Nga -0.78 deri 2.085. So that's where we're going to select. And now here we have another antenna where d is equal to lambda, and in this case, the values of z will be selected from -1.085 to +1.085. Okay. Now, actually, this graph, it tells us, makes things much more clear. So an antenna which is equal, which has a distance of lambda over 4, we see that the value of z, it will be, it can be from 0. Okay, so maybe it's better if we do it like this. So this is 0. This is 0.76, but I cannot write. Minus 0.76. I can, but it is very messy. So for a wavelength which is like this, the values of z, they go from 0.76 to 1, and they come back as a function of angle theta. Okay, and what is angle theta? Angle theta is this. So yeah, so we may expect, as a function of the angle theta, power distribution, which can be evaluated by substituting these values in the Chebyshev equation. Now, this was the second case where, actually I have to draw this better. Let's assume this is the z-axis. This is 0. This is okay, so again, from 0, it increases to 1.08, and then it decreases again as a function of the angle theta. When for this type of distance between any two subsequent antennas, we observe that the values of z are going to change from minus 0.7, will increase up to 1.085, and then they will decrease again. So that's what I was trying to show actually. So here we see an increase, and then here we see the following, a decrease. And then here we see that when the antennas are placed at a distance of lambda from each other, the values of z, where the Chebyshev polynomial will be evaluated, will increase continuously, maximum value, and then will decrease. Now, let's see here. I think this table, we've seen this one also in the previous session, even before discussing the binomial distribution of the excitation coefficients for antennas, or the Chebyshev polynomial distribution. So we've seen this before, and whenever we construct this type of antennas, we have actually different, not different, we have a couple of important parameters, where one of them is Dmax, and the other one, it is D-optimal. This Dmax, it is given by this expression, which is shown here. And let's try to understand how we get this. So Dmax, it can be smaller or equal than lambda divided by pi times cosine inverse 1 over z0. Let's try to observe this, z. So, to some degree, what we are trying to report here, we're trying to say that there are some values of Dmax that beyond this Dmax, we are going to get cosine being smaller than -1, which is not possible, okay? So think for a moment, you're trying to make cosine smaller than -1, that means that before doing that, your Dmax had some specific value. Now, this is the logic how we define this or how we determine this, but what is essential for all of you is you can just write down this equation 6.76a. Okay, with this separation Dmax for a given broadside Chebyshev array with fixed number of element n and specific side lobe level, the array factor maintains the same side lobe level for all. Okay, so again, we're seeing the same thing as we said before, just that if you remember, we used to say that when d was equal to one wavelength, then we can expect the unexpected for the antenna. Okay, when d was equal to lambda or larger than lambda. Now in this case, we have assigned a value for d which should be smaller than Dmax. And as long as it is smaller than some specific value, then we cannot expect that all the minor lobes, they have the same ratio with respect to the major lobe. So they are going to be equal. Otherwise, if this condition is not satisfied, we're going to see an antenna which has a major lobe, and then the minor lobes, they are going to have different ratios with respect to the single largest lobe. So it's something like, this is an element of elegance, an element of having the antenna being equivalent to some degree, because all the minor lobes, they're going to be equal to each other. Now, this was Dmax. Next to Dmax, we can also determine another element, which is the D-optimal, the optimal element separation between the different antennas. And this is given by this expression here. And what we want, what we care is, in fact, is this term, is this equation, because this one we know, right? We're going to set this one initially. This one we know. We're going to say what should be the distance for an antenna that can have n elements, but the ratio between the major lobe and the fundamental lobe is equal to R0. We just substitute all the values in this equation here. We get gamma. Then this gamma we insert here, and we determine what is the optimal distance for between any two subsequent antenna elements. Sorry, why is it doing like this? Okay. Again. And apparently, yes. So design curves for these specific Ds as a function of the side lobe level from these two ratios for broadside. So again, we're given too much information. So we have a broadside antenna. What is a broadside antenna? Is an antenna which gives the maximum distribution along the 0 degrees, along the angle theta equal to 90 degrees. Sorry, this is 90. So this is broadside, but we want coefficients which are Dolf-Chebyshev, and n is n, 20, 10, 30. Now, simply speaking, we have to come to this slide. And this slide is something that it is constructed using numerical techniques. On the y-axis, we see what is the ratio between the d over d optimal, and the unit, it is lambda. So we observe that Dmax, it has to be approximately 0.95 times D optimal, okay? So apparently Dmax, it's smaller, yeah, anyways, where sometimes, yeah. And on the x-axis, we see the side lobe level, which is expressed in decibels, which means that from here, if we want a ratio between this minor lobe and major lobe, which is around 70, then we have to look at, and what is the number of antenna elements. We have 4 different values. This is for n equal to 10, 20, 30, 40. So if we want an antenna where the ratio between the major lobe and the secondary lobe, it corresponds to 70 decibels, minus 70 decibels, and then we want n equal to 40, that means that the Dmax that we have to select for is going to be this value, okay? Similarly, if we want a ratio which is in the order of 20, then this 20, for, let's see, for 30 antennas, we are going to get a Dmax divided by D optical, which is larger than 0.95. So which is going to be something like 0.96 times lambda. Okay. Now again, here we have a similar slide where Dmax divided by D optimal is described as a function of the number of elements. So we have an antenna. Of course, we start with an antenna which has at least 3 components, 3 different antennas, 4, 5, 6, and it goes like this. So it looks like Dmax divided by D optimal, again, is going to be smaller than 1. And this one is described as a function of decibels. So here we can read So it looks like we covered a couple of examples where the number of antenna elements, they were around 10. But then if you want 30 decibels, we go here. That means that here we can read what the ratio should be. Now, we have another way to find the amplitude coefficients. We are given the equations. We just need to substitute the expressions right away, simply without getting too much confused. And actually, this was example 6.9. We solved this one, but this is just kind of a repetition. But once we got whatever we got for the Chebyshev coefficients, you can apply these equations in those expressions to see whether we approach to what we found in the previous case. Now, using these equations, which are shown here, find the amplitude coefficients, this is what we observe. Okay, then now this is antennas. Whenever we talk about antennas, we have expressions that look like this in equation 6.78, and again, this is an expression which is derived in a very beautiful journal with high impact factor, which means that this is something that we can take it right away for granted. This is called the beam broadening factor, which is described by F, and as a function of F, we can also describe the directivity. Now, and then the beam broadening. Now, this beam broadening factor, which is this little f here, we can plot the graph of how the f varies as a function of side lobe level. So it is clear that many parameters, or for many antennas, the ratio between the major lobe and the minor lobes, it is very important. Which in principle, this would mean that we can have a very strong signal sent at a specific angle, but we do not want to disturb receivers using power which can be radiated using the minor lobes, okay? So it's an important factor because we want to keep the antenna shut down at a specific angle range, but keep it on at a specific direction that we select to radiate to. Now here we have the graph which we should be able to read the possible directivities for Chebyshev arrays as a function of array length. Here we have another example. Now, whenever it comes to these examples, it looks like we simply have to, so the question is, calculate the half power beam width and directivity for the Dolph Chebyshev array for a spacing of λ/2. In this case, we just need to substitute the expression in here. We find that this broadband factor f is 1.079, and then we just substitute this f that we found in 2 slides before in here, and we can determine the directivity. Okay, so here we can have some other examples. When I say these other examples, you can have a look at what these are. Now, in designing non-uniform arrays, the amplitude distribution between elements is used to control the side lobe level. Okay, so and actually the amplitude distribution. This figure 6.26. This is the figure, and this gives the amplitude, the excitation amplitude distribution for Dolph Chebyshev arrays, each with a specific number of elements and at a specific distance as a function of the wavelength. Now, we covered relatively some good amount of material, and all of this, it was all from chapter 6, and we observed that there is quite a few of work in here, but a good antenna designer, what has to do is just to go over a good textbook or a good manual and try to read that manual carefully and implement the given parameters to determine the antenna sizes. Do you have sizes and other parameters? Do you have any question? Now, we said before that we can have antennas which are broadside, which is this and this. We can have antennas which are fire end, which means that we're going to have distribution this way. But we can have also scanning. And now this scanning, it will be made possible for power distribution, which can go, let's say, at an angle of 60. In this case, we have to be careful regarding the equations. They are not as simple as we might expect, but this phase difference between any two subsequent antennas to produce this distribution of the power along this specific direction, okay, so this is theta 0, we will have to use these expressions, which we have seen this quite a few times. And then the Chebyshev design for a scanning antenna has the array factors as given in these equations, which we can substitute in here, and then but we just substitute the values, and then we can determine important elements that we need to design this beautiful antenna, which has this specific orientation, as in here. For example, we can have an antenna which is not broadside, but it can be directing the power in the angle of 60 degrees. We can use the expressions which are given here, and if we notice, we see that these equations, they're pretty much similar to the expressions that we had until now, only that now here we have cosine theta 0. So far, this cosine theta 0, it was something 90 degree, depending on what type of antenna we were dealing, okay? So far, we were dealing with broadside antenna, with theta 0, it's equal to 90, cosine 90 is equal to 0. So this 6.85, around 10 to 15 slides before, this whole expression, it had everything except for the cosine term. Now, we can stop here at this stage. Let's keep these annotations. I want to keep these because these were useful.